What I'm going to deliver is a very, very simple talk, very, very basic ideas, so hopefully everyone could follow it and tell me afterwards that, well, I mean, you don't need to, okay, no, higher, like this. Okay, so let me start with a bit of motivation, because the goal of the talk is to construct a family of what we think are interesting Poisson structures. So why would one want to do that? Well, the situation is the following one. So if you spend a bit of time doing Poisson geometry, well, at the very beginning, it might be very exciting because, for example, if you come from symplectic geometry, you start seeing like some results, like Darboux theorem, have an analog in Poisson geometry, say Weichen's splitting theorem, or that the rank homology is transferred now to the Poisson cohomology. But very soon you realize that there are few global results in Poisson geometry, I mean, which are available for every Poisson manifold. And for example, if you try to, say, ask the existence question, right? So let me write this, that Poisson geometry lacks global results. So pick a manifold, M, and ask whether it supports a Poisson tensor, a Poisson structure, and the answer is yes, because I mean you can put the zero Poisson structure, right? So the questions of existence is a bit trivial. So next, you can ask for a bit more, and there is Poisson tensors which have non-trivial support, and you also realize that that's very simple because using two-dimensional Poisson geometry, you can produce Poisson structures which are basically localized on open subsets. So what you have to do is refine the question and ask for the existence on a given manifold of Poisson structures with some interesting properties, whatever that means. So you have to refine to existence of, let's say, interesting Poisson structures. So another manifestation of the problems that we have to say something interesting globally about Poisson manifolds comes with the cohomological and homological invariants. So we do have Poisson homology and cohomology, but it's almost impossible to compute it but in a few cases. So these invariants are hardly computable. And perhaps the only exception in which people devoted a lot of effort is in computing the modular class, right? So perhaps, maybe the modular class is more transparent. So, well, I mean, what to do? What do we have to do in this situation? Well, look for interesting classes of Poisson manifolds for which we can say things which can answer interesting questions and not only answer them, but give an interesting response. Okay, so what are these classes of interesting manifolds, interesting Poisson manifolds? Well, that goes a little bit according to taste, but let me present some examples of those. So the first class is a generalization of the following example. So take the sphere, consider the height function, and consider the following Poisson tensor. Yes, I'm using the height function as a coordinate, and also I'm using the angular vector field. And well, what you get is a Poisson structure with the following symplectic foliation. So every point in the equator is a symplectic leaf, and then you have the upper and the lower hemispheres. Now, this is an example. I mean, actually, what's interesting is to write first of all, the symplectic form, And you see, if you write the symplectic form, you have something which is not defined in the equator because it goes to infinity. And now the interesting idea is that what you can do, so this is not a section of the second exterior power of the tangent bundle, of the cotangent bundle, but what you can do is replace your tangent bundle by a different vector bundle. So you basically take the B tangent bundle associated to the equator. So this is a tangent bundle whose associated locally free sheaf is given by those vector fields which are tangent to the equator. And it does happen that when you do this inversion process, what you get is something which is honestly a section of this second exterior power of that tangent bundle, of that cotangent bundle. And well, that actually is not just a cotangent bundle, I mean, but it's basically that the rank complex induces here also a complex. And the outcome is that what you have here is something which is closed and non-degenerate. So it's a symplectic form, but associated to something different from the tangent bundle. Now, because it's closed and it's non-degenerate, it turns out that most of the techniques, differential geometry techniques in symplectic geometry, mostly Moser's trick, are valid in this setting. So let me put that more generally. The way to generalize this example is that you have, on a manifold of even dimension, you have a Poisson structure. This Poisson structure, when you take the top exterior power, so that's a section of a line bundle, the line bundle dual to the line bundle that hosts volume forms, and you're asking this section to vanish transversally. And well, that's what people call a B-symplectic manifold or a B-symplectic structure. And all these structures are, to a large extent, they are controlled by, let's say, symplectic geometry. And to a lesser extent, by symplectic topology, meaning that there are some, let's say, gluing techniques that come from symplectic topology that you can transfer to this setting. And, well, there has been lots of recent papers around this kind of Poisson manifolds. All right, so second example, second class of interesting Poisson manifold. So take the linear Poisson structure on the dual of ACU2. So here you have the symplectic foliation given by the spheres. And, well, that's an example of a very interesting Poisson structure. You can complicate it a little bit more. So you can take a base symplectic manifold. For example, you can take, I don't know, a symplectic surface. You can take a principal bundle with this group, and you can take the associated bundle. And this associated bundle basically supports a Poisson structure that comes from the linear one here and from the symplectic form here. So this is an example of what we call a Poisson manifold of compact type. And it's good that Daniele mentioned this name several times in his talk. And, well, the interest of this kind of Poisson manifolds is that they are, to a large extent, they are controlled by Lie theory of compact groups. And by integral affine geometry. And as in the case of B-symplectic structures, we can ask interesting global questions about these Poisson manifolds, and more importantly, we can answer them. All right, so third class of Poisson structures, which are really the topic of this talk. So let me actually distinguish two subclasses. So these are Poisson-Lie groups, or not quite Poisson-Lie groups, some part of the Poisson structures that can link to Poisson-Lie groups. So remember that the Poisson-Lie group is a Lie group that has a Poisson structure which is compatible with the multiplication in the sense that the multiplication map is Poisson. Now, these structures, they are, again, to a great extent, they are controlled by Lie theory of bialgebras. Let's just say Lie theory in general. Now, I'm interested in not any Lie group in this talk, but the case in which G is compact. So again, you can think of SU2. And I'm actually interested not in the group itself, but in the regular coadjoint orbit in K mod the maximal torus. So for example, here, S1. And well, the general theory of Poisson-Lie groups tells us that the coadjoint orbit supports a Poisson structure, right? So in this case, the coadjoint orbit for SU2 is a sphere. Now, why this structure is worth studying, or what are the properties that make it distinguished? Well, the first interesting property is that this Poisson structure, right here, has a finite number of leaves. So you see here this symplectic leaf, and the rest is actually the Brouhat decomposition. The leaves match the Brouhat decomposition of the regular orbit. So if you want a function, if you want a description of the Poisson tensor, you can do or write something like minus the arc cosine of the height function squared times ddh dd theta. Oh, sorry. Plus pi plus 1. And, well, it has finite leaves. Also, it has large symmetry. It's invariant by rotations. And it has another very interesting property. It's a geometric structure on a coadjoint orbit. Now, coadjoint orbits are central to mathematics because you can put all sorts of structures. So the third important thing is that GT or KT is a regular coadjoint orbit. And, well, in a regular coadjoint orbit, I mean, what do you have? You have symplectic geometry. The symplectic geometry of the constant Kirillov-Soriot to form. You have Keller geometry. This Keller geometry comes from the fact that essentially you can build the coadjoint orbit not just using the group itself, but also using its complexification. And, well, I mean, the S1 invariance, I mean, allows you to do all sorts of computations in a very simple way, and also not just the SU2 invariance or the SU2 action allows you to do cohomological computations in a very easy way. So the cohomology is essentially combinatorial, given by the Weil group. So we do have a Poisson structure with all these nice properties in a very beautiful manifold. Right. So just because of that, it's worth being studied. Okay, so this is example 3a, which is, I think, known since the early 90s. So it's been around for a long time. And in fact, I mean, this family has an analog in the commutative world. So these are examples, or interesting examples, for compact, essentially semi-simple Lie groups. Now, if you go to compact abelian groups, what you have is toric varieties, right? So let me describe for you the standard toric Poisson structure. So these structures, I think, so they appear kind of in disguise in a paper by Rui, Ratiu, and Ortega, but I think the person that studied them in more detail is Arlo Kane in a paper of 2009. So this is the standard toric Poisson structure. So let me illustrate it with the simplest toric variety, which is, again, the sphere. Now, this toric Poisson structure is given, for example, by the following Poisson bivector. And it's also a Poisson structure that has a finite number of leaves. And these leaves are very much linked to the toric structure, because if you look at the image of the momentum map, essentially the stratification by a finite number of leaves matches or is the pullback of the stratification of the polytope of the toric variety. So you have like the 2 points that correspond to the boundary points of the interval, and then you have the open symplectic leaf. So again, so why interesting? First of all, because it has a finite number of leaves. So you see, this is a funny thing, because finite numbers of things on a compact manifold, it means that you are finite number of open leaves. So you are, well, with the exception of the points, you are kind of like assembling things that very often they have global Darboux coordinates. So you are assembling a standard linear symplectic structures in such a way with a finite number of pieces that they match into a Poisson structure on the total space. So by the way, let me just tell you, I forgot to say that the singular points, I mean, the Poisson structure has a quadratic elliptic vanishing there, so there is no linear part present. So they have finite leaves. Second thing, they have a large symmetry. In fact, the symmetry is even larger than in the case of Lie Poisson structures, because here the whole C star acts by symmetries. And the third thing is that the variety that hosts this Poisson structure is extremely interesting. It's a toric variety. It's a toric manifold. And of course, on a toric manifold, we have symplectic geometry, the symplectic geometry of any of the standard symplectic structure. No, the reason why I want to call no, I don't want the other. I don't call the other one torics because I mean they come from semi-simple Lie groups, so they come in the non-abelian setting.
But there is still an S1.
Yeah, but that's not really.
S1, it's not in SU2. It's completely different.
It's different. It's different in the. So it has to do with from where they come from. So one comes from the non-abelian setting, the other one comes from the abelian setting. It's true that you see, this manifold has a K symmetry, but only the T symmetry survives in the quotient for the Poisson structure. There, well, I mean, the construction is such that the structure has this invariance. Even more, there you have standard complex structures, and if you look at the symplectic leaves of this Poisson structure, they are not Keller, they are not of type 1-1. Whereas in that scenario, what you have is leaves which are Keller submanifolds, right, with respect to the global complex structure. Okay, so this has a symplectic geometry of the natural symplectic structures. This also has the Keller geometry of the natural complex structure. And, well, I mean, again, since you have this large symmetry, well, we know that symmetry can be used to compute the cohomology, to compute a number of things, right? All right, so what was the goal of Lilian and myself when we started with her PhD problem? So what we wanted to do is the following. So given the lack of, let's say, like interesting examples, or I mean, given that it's important to produce distinguished examples of Poisson manifolds, what we wanted to do is, using these two families, construct Poisson structures with some similar features in bundles with base one of those structures and with fiber the other one. So let me simplify the question as follows. So take the non-trivial bundle over S2. And for example, think that your S2 in the base supports the historic Poisson structure. And suppose that your S2 in the fiber supports the Lie Poisson structure, or maybe also this one, doesn't matter. So the question is that there exists a Poisson structure that somehow reflects the features of the base and of the fiber. So in particular, finite leaves and large symmetry. All right, so that's the question that I wanted to ask, that I want to answer in this talk. So present you a construction of such Poisson structures. And for that, as you can imagine, I need to go over the notions, actually, of what could be a fibration in Poisson geometry, right? Because, I mean, this being reflected, being linked to the base and the fiber means some sort of fibration property for the Poisson structure. So what is a fibration in differential geometry? Well, it's a space that generalizes a direct product, right? I mean, locally, it looks like a direct product from a piece in the base times a fiber. So you can, in a very naive way, define what is a locally trivial geometric structure as long as that geometric structure is closed under Cartesian products. So, for example, you can do that for symplectic structures. You cannot do that for contact structures. You can do that for Poisson structures. So let me start with that very, very naive definition. I'll call it locally trivial Poisson structure. Let's say over the Poisson base, B by B, and with fiber F by F. So, well, you have your manifold M, which is fibration. So let me ask one property. So I want the structural group to act trivially on the leaf space of the fiber. What I'm going to demand for this locally trivial Poisson structure is the obvious thing. So I'm going to ask for the existence of an open cover of the base which trivializes the Poisson structure. So Q minus 1 of ui pi is diffeomorphic to ui pi b times f pi f. Right? And let me simply point out two consequences of this definition, two obvious consequences. Perhaps, let me just call this condition star. So the first obvious consequence is that obviously the projection map is Poisson. I'm about to say it now in the second condition. No. So by star, and I'll say something else about that. By star, you have an obvious bijection between the leaf space of the Poisson structure in your total space and the product of the leaf spaces of base and fiber. So that means that every symplectic leaf over here fibers over a symplectic base in the base with fiber symplectic leaf in the fiber. So it's in some sense like the differential topology's viewpoint for what you would like to see in a fibered Poisson structure. You would like at least to have the analogous notion of fiberation for the corresponding Stefan-Sussman foliations. Now, you can weaken this condition to say that the action preserves or you can remove this condition, but then you get some monodromy, and then you don't get an identification between the leaf spaces of the total space and the product of the leaf spaces. I want this because, for example, I would like to put structures here that have 1, 2, 3, 1, 2, 6 leaves. Things like that. I will have to have very precise control on the symplectic foliation of the structure in the total space. Yeah.
Would we just looking at this Poisson structure as algebroids and looking at the kernel?
No, I don't want to do that for the one reason, is that the maps in Poisson geometry, the morphisms, they go in the wrong direction. They go, right? I mean, you can say, what is a Poisson morphism? And if you try to generalize this for general algebroids, the generalization is going to be a little bit complicated. There's even more. Let me actually tell you what's the right definition, because what I'm saying right now is things which are locally trivial, but I want to weaken the definition. And for that weakening, I'm going to need a notion of what's the meaning that a Poisson structure, say in the total space of the fibration, induces a Poisson structure, and a specified one on a fiber. And that for a Poisson structure, you have several ways of saying that. For a Lie algebroid, it's not that clear to me. I mean, there are other ways, but I'm not sure whether that matches what Olivier was saying this morning. All right? Yes. Yeah. All right, so this definition is a very strong requirement. And more importantly, what's doing here is hiding some very flatness issues that you're going to have in a weaker definition, which is more interesting and which happens more often. So it's hiding flatness. Features. All right, so let me also, so this is locally trivial Poisson structure. Perhaps I would use number 1. Let me go to number 2, basically by reviewing some classical notions of fibrations in Poisson geometry. I mean, what people have been using so far. So what is a classical fibrations? In Poisson geometry. Let me just classical Poisson fibration. So in a Poisson fibration, basically the only information that you give yourself is a Poisson structure on the fiber. And what you want to get in your locally trivial bundle is a vertical Poisson structure that basically induces on each leaf the given Poisson structure. So this is always a vertical Poisson structure. And I mean, you can write down this condition in terms of morphism very nicely, because you can say that you have inclusions from the abstract fiber with image the fiber over any point, which are Poisson morphisms. Right? Because, I mean, your fibers are saturated by symplectic leaves. Now, what if you want a Poisson structure which is more complicated than a vertical one? So, Poisson structure that has larger leaves. So, really the issue here is to say how a Poisson structure induces a Poisson structure on a submanifold. And there are, we know, several ways of doing that. So one possibility, for example, would be to say, okay, so let's say that we have a Poisson structure in the total space with the property that the fibers are Poisson transversals. You could do that, but then the price to pay is that your symplectic fibers on the total space are too big. In particular, they project onto something in the base, which is going to be symplectic, right? And we don't want that. I mean, we want Poisson structures in the base which are very different from being symplectic. We want them more complicated. In other words, the Poisson structure in the base is by no means homogeneous, as it is a Poisson symplectic structure. And okay, so let me try with the following definition, which I would call, for lack of a better name, a fibered Poisson structure. This is a fiber Poisson structure over B, PB with fiber F, PF. All right, so I'm going to start with a fibration such that the condition star there that I wrote is satisfied, so that, and then I'm going to demand the Poisson structure on the total space be of the following type. So the first obvious condition, as you can imagine, I'm going to demand the projection map to be Poisson, right? That's, I mean, if you really want the Poisson structure to influence the Poisson structure in the base to be linked to the Poisson structure in the total space, that's the only option you have. Now, how do we write down that the Poisson structure in the fibers is, there is an induced Poisson structure on each fiber that matches this one? Like I said, there are several possibilities. So one can try with the following one. So for each point B in the base, we have the corresponding inclusion from the abstract fiber into the fiber over B, and for each function in the abstract fiber, what we have is an extension of a function to the total space, of course, with the property, like I said, the extension property. And such that when you compute the Hamiltonian of the extension and restrict the Hamiltonian to the fiber, this is essentially the Hamiltonian of the renal function, right? So Hamiltonians on the abstract fiber, I mean, you put them inside the fiber over B, and they are restriction of Hamiltonians of global ones. Note, by the way, that I'm saying that there exists here. It's not for all functions. Now, I only need, or I only require for a given function some extension. Note also that this definition, I'm not requiring any kind of, let's say, like a smoothness in the choice of the base point. It's for any point B. And this is justified because, I mean, again, if you have something in the base which is Poisson non-homogeneous, the only thing that is reasonable for you to require is that this choice is smooth over B's in the same leaf, but of course not over B's in general around the given point, right? And let me write down a third condition, which is the following one. I'm going to write that the symplectic foliation of this Poisson structure is equal to the foliation F. Now, where does foliation come from? Well, I mean, this condition of the structural group of this bundle being tangent to the leaves of the symplectic foliation of F implies that, I mean, without Poisson structure or anything like that, you have an you have an Stefan-Sussman foliation on the total space. And what you're saying is that I want my Poisson structure to have the same symplectic foliation as this Stefan-Sussman foliation. You can work a little bit and see that, I mean, the Stefan-Sussman foliation is here. And essentially, what happens with condition 1 and 2, it may happen that this foliation here, this symplectic foliation, is too big, in the sense that tangentially, you not only reach directions inside of the symplectic leaves of pi f, but also transversal directions. So you really have to impose this condition. I mean, like I said, this one happens for free, right? And again, let me point out that this condition is also saying that you can recover the Poisson bracket in F out of the Poisson bracket in the total space. So this means that for two functions f and g in the abstract fiber, what you can do is take the bracket of the extensions, restrict it to the fiber over B, and you recover the bracket. Okay. Again, let me point out this again. Because this is a choice for any function, another one, the subset of functions that you're selecting here is not a Poisson subalgebra, right? So you really need to know that this fiber already hosted a Poisson structure to know that you have this equality, right? So this is not, okay, so this is a funny way of saying that it's not that this guy is, let's say, prescribing a Poisson structure or giving a Poisson structure in the fiber. I mean, you really need to know in advance that the fiber was Poisson, right? Okay, so we have this, say, like this naive definition of locally trivial Poisson structure, classical or like more common definitions that we know from the literature of Poisson fibration and this fibered Poisson structure. So, okay, so let's test this definition against the two extreme cases that we know in Poisson geometry. Let's see what happens when we demand base or fiber to be symplectic or the zero Poisson structure, right? To see whether the definition makes sense at all. So let me also, for people who like to work in coordinates,
why isn't it reasonable to ask for the inclusion of the fiber to be like, for you to pull back this ambient thing to the, how's it called, like this Poisson-Dirac submanifold or something?
as a Poisson-Dirac submanifold.
Yeah, that you just pull back pi to the fibers and you get pi f.
Well, I haven't thought about that. So in some sense, what you were possibly saying is that these are kind of like restrictions of admissible functions or something like that. I mean, these extensions that you are putting there. No, maybe that's another way of phrasing things, right? I mean, in any case, I prefer to. It's different. So what do you get then? Yeah. So you see, I mean, the problem with this business is that you can, when you're doing Poisson geometry, you can think like in the larger world of Dirac, or you can think in the algebroid world. And sometimes things go in different directions. So when you try like to mimic things, you don't know what you get. I'm sticking to this point of view because, I mean, this is, at least for me, the one in which I stay closer to geometry and I see really what I'm doing. But there might be alternative definitions or different ones that keeps you also interested in things. That I don't know. I mean, this is work from the last 3 weeks. So it's not refined whatsoever. So one observation for people who like local computations, simply, I mean, if you trivialize the fiber bundle as a fiber bundle, of course, I mean, you can decompose your Poisson tensor into a horizontal part, a mixed part, and a vertical part, and you can rewrite these classes 1, 2, and 3 in terms of conditions for these splittings, which to me are meaningless because, I mean, I cannot see any geometry from these kind of splittings. I think that the global approach, in some sense, is more transparent. But people make careers doing local computation, so this is for the students. All right, so let's see what happens with the zero Poisson structure. Now, if you apply, if you look at this kind of fiber Poisson structures over the zero Poisson structure in the base, what you immediately see is that you recover the notion of a Poisson fibration. So a Poisson fibration is one of these things in which the base is a trivial Poisson structure, which among other things is homogeneous, so it gives you much more space to do things. So this is the same thing as a Poisson fibration. So if you put the zero Poisson structure on the fiber, so I don't have a characterization. I cannot tell you that it's anything known. Let me just simply point out that the symplectic foliation, of course, each symplectic leaf maps diffeomorphically by the projection on the corresponding symplectic leaf in the base. Otherwise said, all symplectic leaves here are never tangent to the fiber. So I'll just write down this as symplectic leaves, not tangent to fibers. So you see, if you think about the picture geometrically, what do the symplectic leaves of this foliation, symplectic foliation gives you in terms of the fibration? They give you some sort of flat Ehresmann connection, but only above each symplectic leaf. So they don't match into a flat Ehresmann connection for the whole fiber, as it's the case here, where locally you have obvious flat Ehresmann connections, which do extend the Ehresmann connections that you have there given by the leaves, right? So that's why I'm telling you that there are flatness issues all the time. So here you have local flatness. There you have flatness over any symplectic leaf. Okay, so this is the zero Poisson structure. Next, I want to move, so that I only have 15 minutes left, so I have to rush. So next thing is 17, okay, then I'll rush a little bit less. So the next case is the symplectic case. And here I'll assume that both, so I'll speak about a fibered symplectic structure. So what is a fibered symplectic structure? Well, it's an object that all of you know very well, or I would say. So you have a symplectic manifold, symplectic structure on the base, symplectic structure on the fiber. So, so if you translate the definition of a fiber Poisson structure in the symplectic setting, so what are the things that you realize immediately? Well, what you realize immediately is that the fibers, they are symplectic manifolds or symplectic submanifolds. Then what you can do is consider the Ehresmann connection given by the symplectic orthogonals. So if you consider the symplectic orthogonals to the fibers, well, it turns out that the condition that the projection is a Poisson map tells you that the restriction of the symplectic form up here happens to be, this is the pullback of the symplectic form in the base along the symplectic orthogonals, which means that if you look at the difference of the symplectic form in the total space minus the pullback of the symplectic form in the base, of course, what you get is a closed two form. So it is a closed extension of the fiber-wise symplectic form. So it's the typical question that you ask when you want simply to extend, to put a symplectic structure in the total space. But more importantly, normally when you look only at that problem of extensions, you never ask conditions of the kernel of the two form that extends. This two form has maximal kernel because it vanishes on the symplectic orthogonal, right? Now, the symplectic orthogonal will give you an Ehresmann connection, but because it's the kernel of a two form with constant rank, it's a flat connection, right? So this is a closed two form, and its kernel is a flat Dirichlet connection. Right, so and well, that basically tells you that you can classify all these fiber Poisson structures under compactness assumptions on the fiber, because I mean, you know that then what you really have is a representation of the fundamental group of the base in the symplectic group, in the group of symplectic morphisms of the fibers. So F compact means that fiber symplectic structures under the usual equivalence relation that is given by how you choose base point to basically do the parallel transport are the same thing as representations from the pi 1 of the base into the group of symplectic morphisms of the fiber, right, under the usual conjugation relation. Right? So let me just remember very briefly how do you go in this direction. So how out of a representation you construct one of these fiber symplectic structures. So you simply pick the universal cover of the base with the obvious pullback symplectic structure. You cross by the fiber, and you take the diagonal action of the fundamental group that uses the representation of the second factor. That's how you go back. All right, so let me just draw one interesting consequence for Poisson fiber structures. Well, in a Poisson fiber structure, if you take a point over a point in the base, you can look at the symplectic leaf, which we know is a symplectic leaf that fibers over the symplectic leaf in the base with fiber, the symplectic leaf in the fiber. Well, if you do a little bit of yoga on differential topology between the difference of immersion and embedding, because these leaves are immersed, you really see that for each symplectic leaf, you obtain one of these fiber symplectic structures. So in particular, you do get these flat connections along the leaves. So that, again, there's no reason for them to match or to, also they have different dimensions because they are over each leaf. So, right, so there are flatness features everywhere. And that should also tell you that you see, it doesn't look very simple to construct this kind of fiber Poisson structures because this is a very strong requirement, like, you know, having this kind of flat connections or like putting together all these fiber symplectic structures. Now, be it as it may, I mean, one shouldn't despair because, I mean, if you look at your, I mean, the examples, I mean, the Poisson manifolds, the Poisson structures you use to work with when you basically test in examples any sort of theory, you immediately see that, well, they are the most symmetric ones. They are, most of them, they come from Poisson reduction, right? So, and even more, you see, I mean, not only that the structures come from Poisson reduction, in particular the ones that I told you at the very beginning, this Lie Poisson structure comes from reduction, and also the structure on toric varieties comes from reduction. But also, I mean, if you want to get something like that in the Poisson setting, it makes sense to basically repeat this quotient construction, replacing this discrete group by a continuous one, right? So, yeah, so a construction. So let's start with the following data. I'm going to start with two Poisson manifolds. One of them is going to be my fiber, and I'm going to start with a Lie group G, which acts in both of them by Poisson morphisms with the following additional properties. So I'm going to ask that the action of G in N is free and with a smooth quotient. And yeah, the last part is because this group may very well be non-compact. So we'll need to have a smooth quotient. And of course, this is a smooth quotient because this is a Poisson manifold. The action is by Poisson transformation. Is another Poisson manifold. The second requirement is about the action on the fiber. So I want the action here to be tangent to the symplectic leaves. Right? And I'm going to make the quotient and see what happens with the quotient space. Right? So I'm going to take as M the product by the diagonal action, and I'm going to call pi the induced Poisson structure, right? And so let me also point out another thing. I mean, another obvious thing is that in this product manifold that I'm starting with, which I'm starting to do the quotient, of course, the Poisson structures that come from the two factors, pi n and pi f, they commute, right? Which means that I can decompose well, I should call it pi f because, or I shouldn't call it pi f. Pi vertical and pi horizontal, which are commuting Poisson structures. So that's the sum of two commuting Poisson structures at least. And in fact, I should call this pi f. Why not? It's pi f after all. So what do we get with no further requirements? So what do we get is the following thing. You don't need to check anything because everything here is obvious. The map onto the base, of course, is Poisson. Well, I already mentioned that it is the sum of the two commuting structures. And what you think is a slightly bothered thing at the very beginning is that the symplectic foliation may not be the foliation that it descends from the product foliation here, the one that you would like to realize. So everything you can say is that it is contained. And let me tell you what's the problem, what may go wrong, so that we can fix it putting additional conditions. So here's what may go wrong.
What is the second F?
Yes, so it's the foliation that descends from the product foliation here. Maybe n times f. So that comes from differential topology. Just because you have two Stefan-Sussman foliations and you have an action which is compatible with them, go to the quotient, you get a Stefan-Sussman foliation. So that's the one you would like to realize as symplectic foliation, but in principle may not be the case. So why it may not be the case? So really, the problematic thing, the condition that you are not able to get, the property of a fiber Poisson structure that you may not be able to get, is to realize Hamiltonian vector fields of the Poisson structure on the fiber as restrictions of Hamiltonians of global functions. So why is that? So let me try to make a picture. So this is my point in the base. This is the point x, this is a point y in the fiber, and so I will pick a function in the fiber. That function has a Hamiltonian that maybe points in this direction. And what I'm going to do is, well, I mean, to study functions in this quotient is much better to go up to the product and study invariant functions. I mean, of course, that's the one thing you want to do. So I want to produce in a natural way an invariant functions out of a function which is only defined on the fiber. So here I am in the product. So this is the manifold n. So this is a point that sits over the point in the base. In this point, I have point z. So I have the orbit. And what I'm going to do is simply, I'm going to take a slice to the orbit foliation. that I will call sigma. And I'm going to extend my function in a natural way. So this function f is going to extend to the slice by zeros, by the pullback, and then this slice times the fiber is a slice for the diagonal action. So I can extend it by the g action, right? So I do get, so this is by zeros, and then I get a function h, which is g invariant by g invariance. And I'm going to compute the Hamiltonian, right? So if you compute the Hamiltonian of this function, of course, because you are in a product space with a product Poisson structure, you're going to get the sum of two Hamiltonians. So let me actually compute first the differential. So the differential is going to be the differential along B plus the differential along F. Now, when you pass to Hamiltonians, here you get what you expect. You get, at this point, this direction. Now, the problem comes here because, I mean, you may think, oh, okay, so I extended by 0, so this guy disappears. But it's not true because you see, I mean, if you see what happens with the value of the function here, so this function, so let me actually write this. Okay, so let me write this differential. So I'm going to split in directions. So I'm going to split this into directions in the transversal and directions in the orbit. So I'm going to get accordingly two vectors, which is the vector here and the vector here, right? So I decompose the Hamiltonian, so it has two directions. Well, I mean, like I said, why these terms are not vanishing? Because, I mean, when you see what's the value of the function here, I mean, this function is extended by g invariance, which means that it picks the value of the function in the corresponding orbit by the action of the inverse of this element. So it's not a function which is constant on that factor. So it picks what happens here in the fiber. Yeah, that's a problem. So imagine, for example, that you get a guy such that this part is vanishing, right? So if you want to realize, to see what's the Hamiltonian vector field in the quotient space, what you have to do is basically make the component along the orbit 0. If you make it 0, then what appears here, so if this component is the fundamental vector field of the action for the element alpha in the Lie algebra, what you get here is the opposite one. In particular, if you get a direction, if you choose a direction tangent to the leaf here, it may be that it's in the kernel of pi sharp. So that's the problem. You may lose directions along the orbit, along the directions of the orbits here. So again, what we have to do is impose natural conditions so we can control these two summands. So let me, without proof perhaps, because I'm running out of time, it's like 5 minutes. 5 minutes, thank you. So let me put some extra conditions. So this is situation 0, no conditions. This is situation, it's not 1, it's isotropic. So ask G orbits on F isotropic. Now, if you ask the orbits on F to be isotropic, so let me write down what are the consequences. We get a Poisson structure with the correct symplectic foliation. But we don't quite get on each fiber the old Poisson structure. We get Poisson structures which might be different. So FB gets a Poisson structure with the same foliation as the Poisson structure in the fiber, but with maybe different leafwise symplectic forms. That's something we can control. So why is that, for example? Why do we get the same foliation? So you see, I mean, to make sure that you get the same foliation, really the only thing that you have to check here is that when you have a Hamiltonian which is tangent to the orbit, you must make sure that you don't cancel it out by going back. Now, because the orbit is isotropic, it turns out that this Hamiltonian has as potential a function which is vanishing along this orbit. It means that the differential of this extension is going to be also vanishing along this orbit. So in particular, for these directions, you do recover the original h of f, right? So, and I mean, this isotropic condition is very natural because it's always fulfilled, for example, for S1. So if you take a cycle action with that properties, in the quotient you do get a Poisson structure with the right foliation and whose fibers are Poisson or inherit Poisson structures. another condition. So assume that the free action on the first factor, the one that produces the base, is nowhere tangent to the orbits. Then we do get a fibered Poisson structure. Now, briefly, why is that? You see, I mean, why essentially we can extend this function f to a function that is 0 here? You see, because, I mean, here we took an arbitrary slice to the orbit foliation. I don't know. What is? Where? Nowhere tangent. Yes, I didn't say. Nowhere tangent.
There's a P that appears just before, just nowhere.
Nowhere tangent to.
Further left.
Yes, it's n. It was P here. But I didn't want to give you the impression that it was a principal bundle, so, though it's a principal bundle. So, okay, so why we do get that? Because, I mean, you see, I mean, in this case, we can take the slice containing the symplectic leaf over this point. And then, you know, if you want to compute the Hamiltonian only picks information along the symplectic leaf. So if there the function is constant, it's a local, it's a constant function here, then you're done, right? So you get one of these fiber Poisson structures. Okay, so how do we do that for the non-trivial fibration over S2 with fiber S2? So I mentioned, but I didn't tell you why, that these Poisson structures, these two funny Poisson structures on the spheres with finite number of leaves, they are constructed via reduction. So this toric Poisson structure, in fact, it comes by reduction of this Poisson tensor. By reduction, so this Poisson tensor is invariant the action of C star, two copies of C star. So you take the diagonal action and you get it here. In any case, I don't want to take the full diagonal action, the full action by C star. I first want to quotient down by the action of the reals, so I get into S3. So here I'm going to, so let me call this the quadratic structure. So I get the quadratic structure on S3, and then I further down quotient to get my structure here. This Poisson structure on SU2 mod S1, well, it comes also from reduction, but in this case we don't need that because it's going to act as fiber. This is S1 invariant, right? So here you have two Poisson structures which are S1 invariant. The action here is tangent to the leaves. The action here is nowhere transverse to the fiber. So let me try to make a picture of this Poisson, the symplectic foliation of these Poisson structures. This is a Poisson structure in S3, right? This map is the Hopf fibration. So these 2 points are going to give you here the Hopf link. So in S3, right? Okay, so if I draw S3 with a point at infinity, lost, then the Hopf link is this one. But I don't want to use this picture because then I cannot tell you where the other symplectic leaves are because I mean it's actually difficult to draw. So let me just bring the infinity point into the blackboard. So you see, we have S3, we have the link, the Hopf link of zero-dimensional leaves, and then we want an S1 family of symplectic leaves. Now this S1 family, I mean, there's only one obvious thing that you can do here is put the cipher surface associated to this link, which is an annulus. This is what you see there, and that's the structure. This cipher structure actually is not only one cipher structure, it gives you an open book decomposition. So if you push it by S1, it gives you an open book decomposition of S3. So these are under the S1 action. Right? So this S1 action is nowhere tangent to the leaves because it basically transports one to the other. So we are in the conditions to basically get a Poisson fibration. More generally, we can apply this to a product of one factor, which is, we can get this kind of fiber structures where the base is any toric variety and or any regular coadjoint orbit of a compact group, and when the fiber is also either of those. And again, we can realize topologically many different bundles. Of course, there are many other questions to study on these structures. For example, one thing I thought at the beginning would be easier because I thought naively that what I would get here were locally trivial Poisson structures. Then the cohomology would be easy to study because it would be basically Leray argument and things like that. But this is not the case here, so I'm not sure how to go around computing the cohomology. I suspect, though, how one can compute most of the Poisson homology, which is going to be finite dimensional. Also, you can get different Poisson structures if you play a little bit with different groups. You can do the reduction at this level with the S1 action, but you can also do the reduction here with the C star action. And, anyway, so you get on the same, just say this, you get on the same fiber bundle related Poisson structures, which I don't know, I wouldn't know to say whether they're the same or not, or they are totally different, among other things, because, they have the same foliation, but we don't know yet how to compute any of the invariants. And yeah, sorry for going a bit over time, so that's what I had to say.